In this video, we will continue our discussion on similitude and dimensionless parameters. Here, you will see that similitude between a model and a prototype can be achieved by equating pi-terms. Let's take a look at this F-18 Hornet. It can be described by a set of pi-terms. We can predict the behavior of this actual F-18 Hornet over a range of flow conditions with a smaller model in a wind tunnel. This model can also be described by a set of pi-terms. If the model is designed and operated under the conditions that the non-pi sub 1 terms of the model equal the respective non-pi sub 1 terms of the actual F-18, then the measured value of the model's pi sub 1 will be equal to the corresponding pi sub 1 of the actual F-18. This is the theory of models, and it is pretty powerful. Now, this may not be clear to some of you at the moment, but let's go over a simple example with a relatively straightforward geometry. Let's revisit the square bus hatch. Suppose we wanted to predict the behavior of the large bus hatch with a smaller model of it. In a previous video, we obtained the pi terms for this bus hatch, which are shown here. Pi sub 1 is the drag force divided by the product of width squared, velocity squared, and density. Pi sub 2 is the height of the hatch divided by the width of the hatch. Pi sub 3 is the viscosity divided by the product of width, velocity, and density. All three of these pi terms are dimensionless. The model of this hatch has its own pi terms. Here you can see that the model's variables are denoted with a subscript m. Let's first focus on equating the non-pi sub 1 terms, which are called the model design conditions. If pi sub 2 of the hatch equals the pi sub 2 of the model, then this would dictate that the width of the model, w sub m, must equal the width of the actual hatch times the height ratio of the model to the hatch. Is this all there is to modeling? You should all be shouting no at the moment. It's not just about geometry. We also need to consider equating the third pi term for the actual hatch and the model. Doing this will dictate the velocity of the airflow over the model of the bus hatch. Here you see that the flow velocity for the model must be different than the flow velocity of the actual hatch. Even if you're using the same fluid for the actual hatch and the model, such as air, which would result in the viscosity and density ratios equaling 1, the velocity of the flow for the model will equal the velocity of the flow over the actual hatch times the width of the hatch divided by the width of the model. This brings us to a key point, which is there is more to model design than just scaling the geometry. You cannot just take a scale model of something and subject it to the same flow conditions. The flow velocity for the model could be much different than the flow velocity of the real thing. So if the model design conditions are satisfied, and we know the width, density, and velocities of the model and the real thing, then a measurement of the drag force on the smaller model will enable us to predict the actual drag force on the real thing. Therefore, if you are trying to determine the forces on a large system using a smaller model, then all pi terms must be equated between the model and the real thing. Let's take a moment to discuss the dimensionless groups that you have seen thus far. The drag coefficient is a dimensionless form of the drag force. It is a ratio of drag and inertia forces. The lift coefficient is a dimensionless form of the lift force. It is a ratio of lift and inertia forces. In the example in this video, you were introduced to the length ratio, which is the ratio of some pertinent length to the characteristic length. Most importantly, you encountered a very important number in fluids, which is the Reynolds number. The Reynolds number is the ratio of inertial force and viscous force of a fluid. In our example of the bus hatch, you can see that the non-pi sub 1 terms are the length ratio and the Reynolds number. In summary, a prototype and a model can be described by a set of pi terms. we can conduct experiments on the model and measure the pi sub 1m term for the model, and this will be equal to the corresponding pi sub 1 for the prototype, only if the other pi terms are equal for the model and the prototype. Let's take a quiz. Let's assume that you have a 1/15th scale model of a submarine. Submarines belong in the water, but you only have a wind tunnel available for testing. Air and water have the viscosities shown here. Suppose that you run an experiment where you set the flow in the wind tunnel to 55 meters per second. What would be the speed of the actual submarine in freshwater if Reynolds number similarity is a requirement? Please pause the video, work out the problem, and choose an appropriate answer. The correct answer is D. To ensure Reynolds number similarity, the Reynolds number of the actual submarine must be equal to the Reynolds number of the model. Here you see that the velocity of the model will equal the flow velocity of the prototype times the length ratio times the ratio of viscosities of air and water. Plugging in the values reveals that the flow velocity of the model is 197.3 times greater than the flow on the actual submarine. This means that the model, which is encountering an airflow of 55 meters per second in the wind tunnel, is modeling a submarine that is only moving at 0.28 meters per second in fresh water.